I'm going to speak to you on the topic of conventional and organic fertilizer. Let us begin with the question of what is fertilizer. And the technical definition here is any organic or inorganic material of natural or synthetic origin that is added to a soil to supply one or more plant nutrients essential to the growth of plants. Generally, these materials will fall into two categories. The first being conventional, also known as organic or synthetic, and these are manufactured materials. The second class would be organic materials, and these are naturally occurring. Organics or mineral deposits, organics being crop residues, animal wastes, other organic waste products such as ash or biosolids, or mineral deposits such as saltpeter, potassium nitrate, otherwise known as bat guano. But this does bring out a question of, what is the technical definition here, because in chemistry, in most cases, an organic molecule is one that contains carbon. In the case of the fertilizer urea, it contains a carbon and is naturally occurring. But since it's manufactured, we call it synthetic. It's all how you label it. So this begs the question, do I need fertilizer? Well, you will if the crop demands more than the soil can supply. So can the plant tell where the specific nutrient in question comes from, be it from an organic or inorganic source? Well, the mechanisms of plant uptake are very specific in terms of how the plant acquires nutrients. Either material will break down into smaller component parts that result in plant uptake of the nutrient in question. So in essence, the plant cannot tell where the phosphate, for example, came from at all. So let me quickly talk about genotype versus phenotype. The genotype is the genetic makeup of the plant. This is the genetic potential. The phenotype is what the plant actually does in the field under environmental stimuli. These are quite different. You can have the best fertility program in the world and still have an outbreak of disease or poor weather. This will influence your yield. So soil or fertilizer inputs are just a part of the puzzle of crop production. It's not 100% of what you should spend your time worrying about. In addition, there are circumstances such as non-responsive soils where a crop does not respond to fertilizer input relative to an unfertilized check. So in some cases you will not need fertilizer. We'll talk a little bit about that in a minute. So let's talk about crop utilization of fertilizer N. N uptake efficiency varies due to soil supplying nitrogen capacity, weather conditions, which affect nitrogen mineralization and fertilizer mobility in the soil, as well as nitrogen losses from the system. In Illinois, typical uptake efficiency is 30 to 50% of the nitrogen applied, and even with high rates on the good soils throughout the state, at least in the northern two-thirds, the soil often supplies the majority of crop nitrogen. And the proportion of the N uptake decreases during the growing season. There's a progressive depletion of fertilizer N throughout the season due to increased plant and microbial uptake and ongoing losses from the system. Additionally, your fertilizer response is reduced because throughout the season, the nitrogen slowly coming from soil increases, and that's at a steady, or rather dynamic state, but as an ongoing process instead of a one-time dose such as many fertilizers are applied. The key to fertility in terms of fertilizer inputs is to apply just enough for optimal crop response. You can see at this graph, that's the typical law of diminishing returns. The key is to figure out where this point is. And in this case, I would say that on-farm trials, specific on-farm trials for whatever crop you're trying to grow, can help you dial in how much nitrogen in a typical year you will need. Vary your dose, look at the yields, and that can help you modify your program to be more environmentally sound. So there are what we call the essential nutrients required by plants, and these are elements that are required for the plant to reproduce and complete its life cycle, otherwise known as seed to seed. And a requirement of this is no other element may substitute, and the element must be directly involved in the nutrition of the plant. This idea was popularized by Justus von Liebig in terms of what is known as the law of the minimum. And this states that plant growth is controlled not by the total amount of resources, but by the scarcest one. This is typically envisioned in terms of a barrel, staves of varying lengths, and at the point you're filling this up, the nutrient in the lowest supply, or most minimal, will cause the barrel to leak, and this illustrates Liebig's law. So the essential nutrients, the three nutrients would follow these in terms of importance, and these are required by the plant in parts per million or parts per billion, are the micronutrients. There's still some debate as to which nutrients make up these group of micronutrients in terms of being essential, but definitely boron, manganese, copper, molybdenum, iron, and zinc. And there's still some uncertainty about chlorine, cobalt, nickel, silicon, sodium, and vanadium. One point I'd like to make here is you very rarely have to worry about micronutrients. In fact, applying them frequently causes more problems than the application solves. So a typical fertilizer bag. For routine plant culture, the macronutrients will still be the most important because they're required in the most or highest requirements by the plant. For instance, a typical fertilizer bag will have a guaranteed analysis, which is also known as the grade. And what varies on the bag in terms of information is determined on a state-by-state basis, but it usually includes the name, the brand, the trademark, a guaranteed chemical analysis, potential acidity, the manufacturer's name and address, and the net weight of the fertilizer in the container. These are also further delineated as complete or incomplete fertilizers, and this refers to the big three. So a 20-20-20 would be complete versus urea 4600, which would be incomplete. And it's usually, but not always, three numbers. Sometimes in the case of sulfur, there may be added sulfur, as in sulfur-coated urea. You will get a fourth number delineating the sulfur. Here is a hypothetical fertilizer bag. We have a guaranteed analysis here of 10-10-10 of Utilization brand complete fertilizer, manufactured in Branson, Missouri. What you see are three numbers. The first 10 corresponds to nitrogen, and this is the actual 10% nitrogen in the bag. Phosphorus and potassium are expressed differently. You would think that 10 is 10% phosphorus. This is not the case. This is 10% phosphorus in terms of phosphorus pentoxide. There's a big difference in terms of actual phosphorus we'll get to later. The same stands with the example of potassium. It is expressed as the percentage of potassium oxide in the bag instead of the actual percentage of potassium. There are several reasons for this that I won't go into in the premise. So let's talk about synthetic nitrogen fertilizers. Typically, the percentage of nitrogen in the fertilizer, again, is the percentage that the bag actually states. There's also typically more information supplied regarding the nitrogen present in terms of how quickly or slowly the nitrogen is available. Some processes of manufacturing synthetic nitrogen fertilizers result in water insoluble or higher branched chains of nitrogen compounds which are more slowly available because they are not as readily dissolved in water. Many fertilizer bags will state the percentages of both water-soluble and insoluble nitrogen. Water-soluble in terms of response, you generally get about 4 to 6 weeks. Over-application can definitely cause injury in terms of too much vertical growth or fertilizer burn. The slower acting, slower availability of the water insoluble types is much less likely to injure, but you also get a much response. So why does fertilizer burn plants? Typically it's because you put on way too much. So this often occurs because people trust the equipment that they've purchased, that it's calibrated. Many times this is not the case. So I would encourage you to please calibrate your equipment. Learn how to calibrate your equipment. Make sure it's actually putting out what you think it is. In addition, improper post-application handling. Many fertilizers require you to irrigate after application. Failure to do this can oftentimes result in unfavorable results. Also, some fertilizers are more prone than others in terms of their corrosivity. There's a property of fertilizers known as the salt index. Some of them are quite more prone due to this quality to cause damage. I would encourage you to look at the hyperlink I have included on the screen there for further information on that. So quickly available nitrogen, unless it's modified. The advantages are, again, a quick response. It provides nitrogen even when soils are cold, and it tends to be inexpensive because of its high nitrogen analysis. Disadvantages are, again, large flushes of growth. If you put on too much, you can damage plants, and losses are more likely unless you handle the materials in an appropriate manner. Let's begin with anhydrous ammonia. This is the highest nitrogen concentration of any fertilizer currently produced. The advantages are its very high nitrogen concentration. This reduces costs of transport, storage, distribution. It's a very relatively low cost to manufacture compared to other synthetic nitrogen fertilizers, which ultimately tend to be produced from it. The disadvantages are that they must be stored and applied under pressure. It's hazardous to the health. It can be lethal. It's highly corrosive. Safety equipment is critical. It has a drastic effect on soil. Its pH is about 14. It's about as high as it gets. This causes partial sterilization of the soil. It can solubilize organic matter, and it can increase your soil pH to a pH of 9 or higher for some time. Another problem with anhydrous ammonia is it is typically being used for methamphetamine synthesis, and this is a problem for anybody that decides to use this material. Following this in popularity, this is probably one of the most popular fertilizers in the world in terms of nitrogen is urea, fertilizer grade 4600. Urea undergoes enzymatic hydrolysis in the soil and subsequently nitrifies. The advantages of urea are its high nitrogen content. It's very safe, and there's no danger of fire explosion. It will not burn. The disadvantages are it's subject to losses, which can be pretty high as 50 to 80% if not properly managed and if you've put them on the wrong types of soils. Depending on environmental conditions, ammonia toxicity can take place, so you should avoid seeding with urea. And the rapid nitrification can result in losses by leaching if there are precipitation events following the application that are in excess of ammonium nitrate is another synthetic nitrogen fertilizer. Its grade is 3100. It's more available and popular in Europe than the United States. Problems with it: it tends to cake during storage, so you have to break it up before you can apply it, or you have to dissolve it, and the cakes don't really dissolve that well. Half the N is nitrate, so you can get leaching issues. It has a fire and explosion hazard. This is what the IEDs are made from overseas, and as such it can be very difficult to obtain without some sort of licensure or scrutiny from governmental sources. Ammonium sulfate, here we have the added number on the analysis, 210024. One of its advantages are it's acidic. There's no need to incorporate it to reduce losses. This also slows nitrification because the microbes responsible for the nitrification process do not like acidic conditions, so that tends to slow down the process. It also supplies sulfur, which can increase yields, good physical handling properties. Problem with this material is it has a relatively high salt content, and it can cause injury to above ground plant parts if it comes into contact with them and is not washed off. And it has a pretty low nitrogen concentration, so your application rates are pretty high to get moderate doses of nitrogen into the field. A lot of bags will be used. Another class of synthetic nitrogen fertilizers, the ammonium phosphates, monoammonium, diammonium, and ammonium polyphosphate, MAP, DAP, and AP, as they are called. The advantage here is that these materials provide phosphorus as well as nitrogen. The problem is if you use these as your sole source of nitrogen, that you can overapply the phosphorus, which can definitely result in negative environmental consequences. Another class of nitrogen fertilizers are called slow or controlled release. Controlled release sources are a relatively newer class. These are polymer coated designer polymers, and you can selectively coat particles or granules of fertilizer, and basically depending on temperature, this results soil temperatures, this results in anywhere from 70 to 270 days of slow release of nitrogen into the system. Another class would be a slow release, which would be urea form, sulfur coated urea, polymer coated sulfur coated urea, isobutylene diurea, or water insoluble nitrogen. These all have their benefits as well as their weaknesses. I think as time goes on, we'll see a lot more in the terms of controlled release in reducing environmental impact and increasing crop response, but that remains to be seen. The advantage of these kinds of, and almost all of them are urea based, and nitrogen fertilizers are a more uniform growth. They're not likely to cause damage unless you use them in extremely high amounts. Losses through soil or air are much less likely. The disadvantages here are that the release tends to be based on soil temperature, so they may not work on cold soil. Some of these can be pretty expensive, so in terms of acres and acres, it may not make much sense, but prices are coming down even for the controlled release materials. And you may not see quick plant response depending upon which one you use or how they're formulated. Another nitrogen source that's being utilized in recent times here would be stabilized synthetic nitrogen fertilizers, and these are nitrogen fertilizers formulated to include compounds intended to decrease nitrogen losses and therefore increase fertilizer nitrogen use efficiency. These are almost always urea or ammonium based, and these are blended with other chemicals which will reduce the conversion of the parent chemical to one that is subject to loss. Such examples of these chemicals would be an N-butyl thiophosphoric triamide, or NBPT, or dicyanddiamide DCD, which is basically urea base that breaks down into urea, but use by itself be extremely prohibitively expensive. One thing I like to point out, stabilized does not mean slow or controlled release. All this means is that the fertilizer has been modified with compounds that reduce things that affect the transformation of the parent compound into forms that are subject to loss. So, for instance, nitrification inhibition or urease inhibition. These two compounds that are examples here do that separately, and they may or may not work. And in fact, sometimes they can decrease yield because of reasons I'll get into in class. The problem here is cost can be a concern. These can be expensive, but again, the price of these are coming. Let's move on to organic nitrogen fertilizers. This was the majority of nitrogen that was used. Most farms were integrated with an animal operation prior to the 1920s. These a wide variety of materials. Typically they have a very low nitrogen content. There's an idea that you can't over apply organic nitrogen fertilizers. Yes, you can. They're still fertilizer. They may be slow, but if you put on enough, they will pollute. Don't think that they're not. These are not the solutions some people make them out to be. It's just another tool in the toolbox. They can have severe negative consequences if you mishandle them. Typically, animal manure is of local importance because shipping it tends to be very expensive. But if you're local to a confinement operation, disposal is a problem and you can obtain it fairly cheaply. The nitrogen content depends on the kind of animal, be it chicken or hog or what, the feed and bedding material, and the method of the manure handling, storage, and application. The average nitrogen content is 10 pounds of nitrogen per ton, or 0.5%. It's important to know that 50% of this N is available in the first year after application. So if you're putting on that much, realize it's probably just supplemental. Don't rely on doubling it up to get 100% because that's not the way this works. Another thing is sewage sludge. This is pretty popular. It's a byproduct of sewage treatment plants, and again, it's something that the treatment plants want to get rid of. So typically this is treated to reduce pathogens, odor. It's still pretty offensive even though they've reduced the odor, and they reduce heavy metal concentrations within EPA guidelines, however that makes you feel. And they add lime to precipitate the heavy metals. It can be subject to digestion and dewatering to make it a little bit lighter for transport and less stinky. The extent of treatment varies. You get generally two grades. Class A is the better grade with no restrictions in general, so it could be used anywhere. Class B is restricted use. But one thing to realize is that both classes are not tested for radiation or pharmaceuticals, which they can and probably, in terms of pharmaceuticals, contain if you went looking. The nice thing about them is that they contain complex organic nitrogen compounds. They break down at varying rates, and they contain a portion of it is inorganic nitrogen, such as ammonium. So adds a quick release component to this material, and they also contain most other macro and micronutrients, which can be a benefit. Sewage sludge, the nitrogen concentration is variable. The application rates are determined by the crop you're growing, and then the content of plant available nitrogen in terms of nitrate nitrogen or ammonium nitrogen. Typically this is adjusted for volatilization losses. And how do we determine what the release is? Typically incubations are employed. Just like manure, phosphorus content tends to be high. If you use this for all of your nitrogen, you're going to wind up with a lot of excess P, which can cause some serious problems in terms of water quality to the surrounding area. And determining on what material you use, heavy metals can be a problem, and the content often determines how much you can put on and how long you can put it on for. Cover crops, green manure. You can use this for a summer cash crop or use it as a winter cover. Plant in the fall, kill or harvest it in the spring, either by plowing it under or combining it into hay or what have you, or killing it with herbicide. Now, all the N is plant available, and you'll probably need supplemental N. Be advised that non-leguminous crops don't supply much N. Nice thing about the cover crops is you get reduced nitrate leaching from the soil through plant assimilation as the cover crops grow. This does increase organic matter, probably one of the nicer things about it, and they can reduce erosion, which is another nice reason to use. Another class of nitrogen fertilizers that are organic are animal byproducts, and these are products of the slaughterhouse industry. This includes blood meal, which is the highest nitrogen concentration of all the natural organics. Tends to be about 12% nitrogen, with a little bit of phosphorus and potassium thrown in for good measure. Bone meal is crushed up bones. There can be a little bit of nitrogen there. Feather meal from chicken processing. The problem with these products is they tend to be very offensive in odor, unless you like that sort of thing. Most people that have to use a lot of bags of this, and you will if you choose to use it as your sole nitrogen source, you won't use it again. They can be pretty expensive, and unless it's blood meal, it's extremely slow release. But it does release, and it's not that it's not useful. It can be. And then again, there's mineral forms. Nitrogen doesn't normally occur in mineral forms in nature, except as fixed ammonium in rocks and clay minerals, and this means that it's not available. But it does occur as nitrate salts in arid regions. We have Chilean nitrate, nitratine. This is no longer really used, but I just want to bring this to your attention. Sodium nitrate. This occurs in Chile. It also occurs in Death Valley, California. And there's substantial nitrates in bat guano. This is mined from caves, and it's basically potassium nitrate. Let's get back to the bag in terms of fertilizers that contain phosphorus. So does that number on the bag represent the actual amount of phosphorus? And the answer to this is no. This represents phosphorus expressed as phosphorus pentoxide. So if you want to get the actual percentage of P, you have to multiply a given weight by 0.44. This is because P2O5 is not 100% P. You've got some oxygens also in there taking up space. So for example, a 50-pound bag of 020 contains about 10 pounds of P2O5. But the actual amount of phosphorus in the bag then would be 4.4 pounds of phosphorus. So let's talk about the seasonal uptake of phosphorus by plants. Unlike N, phosphorus is taken up throughout the life of the plant. And it's strange in terms of the evolution of plants in that the early growing season is the most critical in the life of the plant. And it's a paradox because phosphorus is required for root growth, but root growth also limits phosphorus uptake because it's consuming phosphorus as the root grows. So the root system is not well developed in seedlings, but the most critical time is when the plant is a seedling. You may have seen purple corn in the fields in the spring, and this is because cool weather slows plant growth. Also, that slows root growth. So this results in a phosphorus deficiency, and this is a typical purpling color that you'll see. So next time you see purple corn in cool weather, you'll notice. Let's go to organic phosphorus fertilizers. We'll begin with animal manure. This accounts for the most organic P applied to cropland. Also contains inorganic phosphorus. As before with nitrogen, it depends how much phosphorus, which type of animal. Typically, there's a high content of total inorganic P in poultry manure. It's also dependent on feed. How long the material has been stored also changes the amounts of inorganic or organic phosphorus. The general composition for manure is 0.5, 0.25, 0.5 by weight in terms of fertilizer analysis. Available phosphorus less than 2 pounds per ton. High levels of available P in heavily manured soils. If you rely on manure year after year after year, you're going to wind up with an excess of phosphorus. Back to sewage sludge, also contains phosphorus on a 2 to 4% dry weight basis. Most of the phosphorus is inorganic. Typical applications will supply excessive phosphorus needed for crop productions, and again we can have heavy metal problems with rock phosphate is an important phosphorus fertilizer in the United States till the 50s. It's still used in the tropics. This is a mined material from phosphate rock reserves in the United States, Florida, North Carolina, Utah, Idaho, Tennessee. It's obtained by strip mining or shaft mining. Very limited phosphorus fertilizer value unless the soil is below pH 6. If you apply this, there's a lot of people joke that you won't see it in your lifetime, or the plants won't see it in your lifetime. The release depends on the fineness of the grind. The finer the grind, the quicker the phosphoric acid is made from rock phosphate, chemical processing. Very high fertilizer grade 050. It is of some use in fertigation, but it tends to be pretty corrosive. It's kind of nasty, so its main use is in the manufacture of other phosphate with better properties. So single superphosphate, aka ordinary superphosphate or normal superphosphate, 020, 012, 8.6% phosphorus. It was the leading phosphorus fertilizer till the 50s. The main limitation was its low phosphorus analysis, and as such it's no longer used in the United States. It's still used in other parts of the world. Triple super, TSP, aka concentrated superphosphate, 0.460, very little sulfur. The high analysis again reduces costs. That's what we're all about. And it's the leading phosphorus fertilizer in the United States to the 50s and 60s available. And we're back to MAP, DAP, and AP. As we talked about before, these contain relatively high amounts of phosphorus as well as nitrogen, makes them quite popular. And it is the reason why DAP is the most popular phosphorus fertilizer. The advantages are they're completely water soluble. Again, high phosphorus content minimizes shipping, handling, and storage costs. And you have a flexibility. You can either solubilize them and apply them as a spray, or apply them as a granule or powder in the field. Another advantage is you have ammonium co-applied with the phosphorus, and this can this actually increases phosphorus uptake when applied with special advantages of MAP are the increased N efficiency. There's no ammonia volatilization or toxicity. It's easy to manufacture. You don't need a high grade of phosphate rock. Polyammonium phosphate, the advantage there is the high phosphate content, high solubility. It's got pretty good effectiveness except in other synthetic phosphorus fertilizer would be nitric and potassium phosphates. Nitric phosphate, fertilizer grade 2020. 50% of the phosphorus is water soluble, best suited for acid soils. The main use of this is overseas. Potassium phosphate, there's two types. Tends to be pretty expensive. So the main use is for small areas or extremely valuable crops. It's got a high P and K content. Phosphorus is 100% soluble. A nice thing about the potassium phosphate is you can apply K without chloride, so you don't have to worry about chloride toxicity, which can be an issue with some crops. And again, cost can be prohibitive. So back to organics for phosphorus. We have animal manure. The phosphorus content tends to be, the potassium content tends to be less variable than that for nitrogen or phosphorus. Lower for liquid than dry. Average composition 0.5, 0.25, 0.5. Available K less than 4 pounds per ton. Another organic K fertilizer would be kelp and seaweed. These contain inorganic potassium salts, potassium chloride, potassium carbonate, etc. These salts will leach into the soil with precipitation. Synthetic potassium fertilizers. These are all mined from mineral deposits. KCl, aka muriate of potash. Fertilizer grade 0060 for the high purity red version, or 0062 for the white. It's the most common potassium fertilizer. It's mined from natural deposits of sylvite in Canada, Saskatchewan. And this material is much less expensive than nitrogen or phosphorus fertilizer. This can be processed with chemical manufacturing methods, K2SO4, sulfate of potash, potassium sulfate, 005017, used on chloride sensitive crops. Again, can be expensive, but then again, if you have a crop that's sensitive, you really can't afford not to use it unless you find a different way. And potassium nitrate, 13044, the main use there is for fruit trees, cotton, and vegetable. Some alkaline K fertilizers: potassium carbonate, potassium bicarbonate, potassium hydroxide. These are good for use in acid soils. They increase the efficacy of phosphorus fertilizer, but again, their costs tend to be pretty expensive, and this is their main limitation. There are potassium fertilizers containing sulfur, potassium thiosulfate, potassium polysulfide. These are suitable for foliar applications of fertigation. Downside is they tend to be expensive. Neither of these are really So in terms of some final thoughts to consider, is there a difference between inorganic and organic? The plant can't tell. Let me just get back to that, where it came from. Again, we're talking about judicious use. We're not talking about let's go out there and hose everything down with inorganics, or organics for that matter. I think the way I view inorganic and organic fertilizers is that they're two tools to be used. If you choose to use them, you can. If you choose not to, you don't need to. But just be advised that they're both out there, and they have both good properties and bad properties. So there's ways to offset possible negative effects. What I mean by there's still a lot to learn is that the fertilizer industry is massive. There's new stuff coming out on a weekly basis. This talk didn't even go into really secondaries or micros. That would be way too long. That's a multi-week course. So I encourage you to go out there and self-educate or ask questions, and just to realize that it goes beyond NPK, even though that's all I touched on today. And really, in my mind, is we're looking for the most bang for the buck, and like the way you're going to get there is to conduct some on-farm trials. Yes, it's going to take up some of your land to determine what rates are optimal, but once you get it dialed in, you just keep riding that horse. So conduct these on-farm trials. I mean, this is the ultimate goal of this is precision farming, is to know the penultimate amounts that you have to use in a normal year. So that being said, if it works for you, it works for you. That's the bottom line. just because the books say one thing. If you're getting good results, I mean, that's all that matters. I mean, you're in this is a business, and treat it like that.